Okay, we'll start. Hello, everyone. Good morning, all of you. So we'll start with a nice quote. It says, "Everybody needs four things in life: something to do." Okay, so if there is nothing to do, you don't know actually why you are living also. And then someone to love. That's very important. And someone to believe in, and something to hope for. Okay, these are all the four things we always need. And today is the birthday of George Parker. Have you heard Parker name at any time? Okay, you will immediately remember. People say Parker pens, right? Parker pens are very famous. So he is that Parker. He was born today, 1863. And George Parker was an American inventor who perfected the fountain pen and founded the Parker Pen Company to manufacture it. Even now, it is a costlier pen actually because it is a fountain pen, and it is very costly. If you, when people many times give present this Parker pen, and he began in a teaching career, which introduced him to the unreliability of existing fountain pens used by his students. So he found the difficulty the people face, the students, with the fountain pen that are existing at that time. And through selling and repairing them, he learned of their construction. And he ceased teaching in 1888. Then he left the teaching to experiment with his own design. And by 8th March 1892, you can see 4 years he has worked. He has resigned the job and he started working his own design for 4 years. And he incorporated Parker Pen Company. He subsequently patented many improvements and was particularly successful in creating a reliable ink flow system. During First World War, his trench pen utilized a tablet pigment to be inserted into the pen and turned to fluid ink by filling the barrel with water. Okay, so he is the inventor of the Parker pen. And there is another celebrity who took birthday today, 1973, Aishwarya Rai Bachchan, because all are familiar about her. I have given her, and very good quote by Aishwarya Rai. Life will take its toll on all of us. We get injured, we get old. It's really sad to try to run away from these harsh realities of life. Looks are not everything. I'm not going to look beautiful all the time. So you can see this type of understanding will make their ego will not be more, right? Otherwise, a celebrity who is beauty of the world must have been having a lot of ego and head weight. But if you have such type of understanding, your personality will be nice. Okay, division of I think it is 28. Right? So in the last class, we have started unstructured grids and we have seen what is the need and use of unstructured grids because all the normal boundaries, the practical problems where we come across the boundaries or domains are not regular. Unless it is a rectangular one, I cannot have a structured grid. And so we need the use of unstructured grids. And what are the steps of developing unstructured grids? We have seen that there should be nodalization and then triangulation. And we have discussed about domain nodalization with example. And then we have seen the triangulation have two methods, advancing front method and Delaney's method. And we have seen what are the advantages and disadvantages of advancing front method. And we have done domain triangulation using advancing front method. And we have seen the applications to simply connected domain, doubly connected domain, and multiply connected domains. Okay, so then the next thing that we have to cover is Delaunay triangulation, right? And it is also the continuation of the chapter 17 of Hoffman and Chiang, volume 2. Okay, we will see what are what is this Delaunay triangulation? And it has advantages. Optimum unstructured triangular mesh. We get the optimum mesh. So I have discussed about what is that optimum triangulation. So I have to have equiangular or equilateral triangles as much as possible. So if you get that, it is more efficient and results in high quality grid. That is the quality. And the disadvantage, difficult to apply for concave domains. So we have discussed about the concave domains. Concave domain means if you have, if you take any 2 points within the domain and if you join them, you should not cross the boundary. Okay. So convex domains are easier or it is straightforward to triangulate, but concave domains usually we split them into two convex domains. Okay, so extra effect is needed to deal with concave domains. Just for example, just 2 minutes.
Okay, I have some problem. Okay, it's okay now. Can you see my screen?
Yes, sir.
Okay, I thought of connecting that board somehow. It has some problem. Okay, I think the last thing. Okay, this is what I wanted to actually draw it, but okay, I have 6 points 1, 2, 3, 4, 5, 6, and if you see, this is the domain. Okay, this domain is it concave domain or convex domain?
Concave.
Concave.
Concave domain, and because if I take 2 points, 1 point here and 1 point here, and if I join, it crosses the boundary. Okay, so that's why it is a concave domain. And so the problem with the concave domain is when you do the triangulation, so what happens is there may be a triangle which comes like this, which is outside the domain. Okay, so the other triangles are okay, but this particular triangle, it is coming outside the domain. So what I may have to do is I have to divide this. If I take 2, 5, right, is the dark line, and then this is one domain, and the lower one can be another domain, and this will be convex domain, and this is also convex domain, and I have to do the triangulation like that. But if I have concave domain, there is a possibility that I may get a false triangle in this. Okay, so that is the problem with the concave domains. Okay, so here to understand the Delaney's method, there are some definitions we make. Okay, so so there is a Dirichlet, right? That Dirichlet condition, whatever we have, that particular Dirichlet in 1850, he proposed a method thereby a domain can be decomposed into a set of convex polygons. Any domain can be divided into number of convex polygons. A triangle is a convex polygon only, right? A quadrilateral is a convex polygon, and each polygon defined as a tile and is associated with a single generating point. Any point inside a tile is closer to its generating point than to any other tile's generating point. So the tile defined above is also referred to as Dirichlet tessellation, Voronoi tessellation, or Thyssen tessellation. So we will see, I will show here. Okay, here this is the polygon. Okay, and A is the tile, and this A, B, C, D, E, F, G, this forms a tile. Okay, and this is the 8 is the generating point. 8 is the generating point. And so here, how this polygon is made is join this point, generating point, to all the neighboring generating points. Okay, these 1, 2, 3, 4, 5, 6, 7 also are the neighboring generating points. So with 8, you join all the generating points. And if you draw perpendicular bisectors to all these lines, okay, so 8E and this DE is perpendicular bisector to 8, 4, okay, and to 8, 3, we draw a perpendicular bisector which is DC, and then 8, 2, CB is the, like that you draw perpendicular bisectors to all these lines, and you are going to get the polygon. Okay, this is a convex polygon that we get with 8 as the generating point. That's what it is explained here. So A, B, C, D, E, F, G defines a tile A, and the generating point is point 8. The boundaries of the tile are perpendicular bisectors of the lines joining the neighboring generating points. Okay, so we have a generating point, join to all the neighboring generating points, and those lines are perpendicularly bisected, and these perpendicular bisectors form the polygon or a tile, okay, with generating point 8. So each point, generating point, will have its own polygon. So here it continues like this, you will have another polygon. And here for 3, there is another polygon. Like that, every generating point, it's have its own polygon. And here the thing is, if you take any point within this tile, within this ABCDEF tile, and that point will be nearest to its own generating point than to the other generating points. Okay, so the 1, 2, 3, 4, 5, 6, 7 are the neighboring generating points. If you take any point in the tile generated by 8, so that will be near to 8 compared to any other generating point. So that is the main characteristic of this. Okay. And Delaunay triangulation that corresponds to the Dirichlet tessellation is constructed by connecting generating points of all neighboring tiles. To relate this discussion, observe that any point inside the tile A should be closer to point 8, okay, than to any other points 1, 2, 3, 4, 5, 6, 7. Okay, so that is the property of this Dirichlet tessellation or Voronoi tessellation or Thyssen tessellation. Okay. Now there are two or three concepts we discuss. Okay. One is swapping. This also we have discussed. So when I have 4 points, these 4 points, if they are joined, we get a quadrilateral, and that can be divided into 2 triangles in 2 ways. Either you can join the opposite corners this way or this way. So you are going to get 2 types, and I have to select the thing which is better one, or which gives me high quality triangles, or which gives me equiangular or equilateral triangles. Okay, if it is not giving, then I have to swap them. That is called as swapping. So for every convex quadrilateral formed by 2 adjacent triangles, the minimum of the 6, how to know whether swapping is needed or not? Okay, this is the condition. The minimum of the 6 angles in the 2 triangles should be greater than it would have been if the alternative diagonal have been drawn and the other pair of triangles are selected. Okay, so we will see here. Now I have this quadrilateral 3, 4, 5, and 8. Okay, listen carefully. 3, 4, 5, and 8. Now I can divide them by joining 4, 8, or I can join them 3, 5. Okay, so I have to see which is better. So what I have to do is, now 480 is joined. See all the 6 angles here. This triangle will have 3 angles and this triangle will have 3 angles. And what is the minimum of that, I have to note down. Then you join 5 and 3. Again, you are going to get 2 triangles. And in those 2 triangles, find out what is the minimum angle. Okay. So which will give me a better combination? Out of these 2 minimum, whichever is maximum, right, that gives me better option, because all must be near to 60, right? So if if there is a very small angle, the other angles are large and it will be away from equiangular property. So the minimum of all the 6 angles for both combinations I have to check, and whichever is more, that combination I have to take up. Is my point clear?
Sir, please repeat.
Yes, sir.
I have one combination when you draw the diagonal like this, 4, 8. Okay. So I got 6 angles. And note down all 6 angles and find out what is the minimum angle. Okay. That is one combination. Then you join 3 and 5. Again, I am going to get 2 triangles like 3, 5, 4 and 3, 5, 8. So I will get again 6 angles and find out which is the minimum. Out of these 2, whichever is higher, that combination I have to take. Okay, what I mean is the minimum angle should not be so less. If it is less, the triangle is not equiangular, right? So it should be near to equiangular, means it should be near to 60. So the minimum angle should be higher. Am I clear or not?
Yes, sir.
Okay, so that is the way I have to choose whether I need swapping or not. How to check is that particular property I have to check. The minimum of the 6 angles in the 2 triangles should be greater than it would have been if the alternate diagonal had been drawn and the other pairs of the triangles are selected. Okay, so that is that example 845 and 834, and another set 835 and 534. That's what I have explained here. Okay,
Sir?
so one combination is 834 and 845, and another combination is 835 and 345. Okay, tell me.
Sir, here E, F, D, C, B, and that points are outside the domain.
No, I am talking about the generating generators, right? The generating points 3, 4, 5, 8. And which is the here nothing like there is. I am not giving the whole domain, right? A domain is a suppose this is the big slide is the whole domain, and in that I have a number of polygons. These polygons are like a small a b c d e f.
Okay, sir. 1, 2, 3, 4, 5, 6, 7. That points are lie in
Generating
another
points.
domain. Another
Generating
domain.
points. Ah, yeah, yeah.
Okay. Okay, sir.
Okay, so it will have its own polygon. Now dotted lines are there, right? So it will have another polygon here, and here another polygon. Here this will have another polygon like that. And each point here is the generating point for its own tile or polygon. Okay,
Yes, sir.
right. Okay, so the algorithm used to generate the locally equiangular triangle is known as swapping. Okay, that algorithm is called as swapping. And how to mathematically do it, I will discuss about that. How to check whether swapping is needed. Okay, just the explanation I have given, right? But how to logically implement in the program. Okay, so that is done like here like this. Okay, if there is a triangle here, there is a triangle here, and there is a point P here. Okay, so when the P is added, I can join these two triangles like either this way that is given in the diagram, or I have to join this way, PB. Is it clear? So how to take up that I have to check. So for this triangle ABC, you draw a circumcircle. You draw a circumcircle. If this point P is within the circumcircle, I need swapping. That is, it is very near to here. If it is very near, I am going to have large angle here, and here these two will be small angles. So I need swapping. So that is, I have to draw a line like this, not this way. Am I clear?
Yes, sir.
So that is the way I have to choose. And so mathematically, at this point, a scheme will be introduced which can be used to determine whether a point P is located inside the circumcircle of a triangle. The procedure is described with reference to figure 17.15, that is this. It can be simply stated that if alpha plus beta is greater than pi, then the point P is located inside the circumcircle. Okay, that is, if this angle alpha plus beta, if it is less than pi, it indicates that it is inside. If it is outside, if you join like this, beta will be less, isn't it? So here, if alpha plus beta is greater than pi, it indicates that this particular point is within the circumcircle. And therefore, a swap is necessary. Okay. And so alpha plus beta is greater than pi means sine alpha plus beta is less than 0, which can be expressed. Sine alpha plus beta is sine alpha cos beta plus cos alpha sine beta. And sine alpha cos beta and those things can be given with the coordinates. Here it is given xab xbc plus yac ybc into xbp yb like this. And xac means xc minus xa, like xmn is xn minus xm, ymn is yn minus ym. In that way, I know all the coordinates of all the points a, b, c, p, and I have to check whether this relation is true. If this relation is true, alpha plus beta is greater than pi, and I need swapping. That's when the criterion previously set by this equation is satisfied. It is concluded that the point P is located within the circumcircle, and note that the required length used are determined like this. And so it needs swapping. Okay, this is the way I have to implement the logic into the program. Because I know all the coordinates, I can determine this particular thing whether this is true or false. If this is true, then swapping is to be done. Is it clear?
Sir,
Yes.
sir, what is XC and XB? Is angle.
Yes, sir.
No, no. XA, XB, XC, YA, YB, YC, XP, YP. These are coordinates of all the ABCP points. This in this triangle. Here, the quadrilateral A, B, C, P are there, right? So coordinates of these 4 points are used to find out the alpha plus beta. The angle alpha and beta are found out using those coordinates. And so if this particular relation is satisfied, it indicates that sine alpha plus beta is less than 0 or alpha plus beta greater than pi. And it indicates that P is within the circumcircle, which indicates that I need swapping. Is it clear? So here XAC means XC minus XA. Here it is given XMN means XN minus XM. YMN means YN minus YM. Here XAC XBC plus YAC YBC into XBP YAP minus, this formula is given, right? So this formula is obtained by substituting the respective sine alpha, cos beta, cos alpha, sine beta in terms of coordinates. So we get this particular relation. If this relation is satisfied, it indicates that the point is within the circumcircle. Is it okay?
Yes, sir.
Okay, right. Okay, that is the way I can understand whether a swapping is needed or not. Okay. Now we will see what is the algorithm for Delaunay triangulation. We will see step by step, and then we will see an example application so that we can understand it well. First, the x and y coordinates of all the n points are normalized. So I am given some points. So these points are to be triangulated. Okay, that is after domain normalization, I got nodes, right? So those nodes are to be taken. So the coordinates are given. And they are normalized with respect to the largest length in the domain so that their values lie within the range of 0 and 1. So I take the largest x coordinate and divide all the x coordinates by that, and largest y coordinate and divide all by that, so that I get everything, all the coordinates within 0 and 1. Okay, that is what is called as normalization. Okay, like your class marks are there, suppose one minor marks. If I divide by the maximum marks that a person got to all the marks that are obtained, so I will have all the marks between 0 and 1. Am I right or not? The highest mark will be 1 and the lowest will be 0. That is called as normalization. And so after doing normalization, there may be some negative coordinates may be there. Okay, I don't want negative coordinates. So what I do is I will try to shift all of them by that point. That is, suppose I have -5 is the x coordinate. Some negative point is there. So you add 5 to all the x coordinates so that the whole thing will be shifted in the x direction. And it comes to the first quadrant. Okay, that is the idea. First quadrant and all points between 0 and 1. Am I clear about this point?
Sir, actually, there is some internet issue, so can you repeat, sir?
Okay, I want all points, all coordinates must be positive, that is in the first quadrant, and I want everything between 0 and 1. So first what I do is I do normalization. All x coordinates are divided by the maximum x coordinate that is present, and all the y coordinates are divided by the maximum y coordinate that is present, so that all xy coordinates will become between 0 and 1. Is that point clear?
Yes, sir. This one is clear, sir. Oh, negative x, how to make to
Okay.
positive.
If there is, that's what. If there is a negative coordinate, suppose -5 is there, the maximum negative thing. Okay. So that is some points are in the second quadrant or third quadrant. Am I right?
Yes, sir.
So if I want to move that whole figure to the right, so what I have to do, add that 5. Okay, -5 is there, suppose. So add 5 to all x coordinates. So what happens? In the x direction, the whole figure will be moved.
Sir, then
Am I right?
Yes, sir.
the values will be shifted after greater than 1, sir. Again, we need to do the
Yeah,
normalization,
yeah.
sir.
No, no, no. Okay, okay. Maybe you do first about that shifting and then you can normalize.
Yeah, yes, sir.
Okay, that's fine. Okay, so what I want is all of them must be in the first quadrant, and all the values must be between 0 and 1. Okay, 0, 0, 1, 1. If you draw a square in the first quadrant, right, all points must be within that. Am I okay?
Yes,
Yes,
sir.
sir.
Right. Okay, so that is the thing we have to do. Then what we have to do is 3 points are added to form a super triangle which completely encompasses all the n points to be triangulated. Okay, I have to take a very big triangle so that all the points will be within that. Okay, because that all are between 0, 0, 1, 1. So I put a big triangle. And so that triangle, it completely encompasses all the n points to be triangulated. And for example, the super triangle can be -100, -100, 100, -100, and 0, 100. Am I clear? So 3 points I will take, okay, a large triangle like this. -100, -100 is in the third quadrant. 100 -2, -100 is in the fourth quadrant. 0, 100 is the in the first quadrant. So I join them a big triangle like that so that all points are within that. Is that point clear?
Yes, sir.
Yes, sir.
Okay. Okay, then create a triangle lista array. So I will have an array created which contains all the triangles. Okay. So first, so it will contain now only one triangle is there, that sober triangle. That triangle you have to keep in the array. Okay, so where the sober triangle is listed as the first triangle. Okay.
Sir,
Yes.
sir, actually, we have transformed the matrix. We have shifted the matrix into the first quadrant, no, sir. But the super triangle, the make by these quadrants,
No,
sorry, by these
that will be outside.
coordinates, so it will be
Okay.
in.
Okay, okay. Just it is so that I how to know what is the sober triangle I can make. So that's why I
Okay,
am
sir.
keeping all the points together in one small bunch, and now I form a triangle like that. So this is outside the first quadrant only.
Yes, sir.
Let it be. Let it be. No problem. Okay.
So, how it will cover the upper triangle, sir? Because it was in first
No, no,
quadrant,
no.
and this will.
See, all are within 0, 0, 1, 1. All points are there. Now I am taking some big triangle, -100, -100 in the third quadrant, 100, -100 in the fourth quadrant, and 0, 100 in the on the y-axis there. And now I join like this so that it is a big triangle which contains all the points within that.
Okay, sir.
Right? Now I will have an array T where I will put all the triangles that are formed. And now first triangle, super triangle is made, and that I will keep in the array. Is it okay?
Yes, sir.
Actually, that doesn't contain any of the points that are actually to be triangulated. Okay, but later we will see how it is done. Okay, now I have one triangle, super triangle in the domain, in the array. Next, Introduce the first point into the super triangle and generate 3 triangles by connecting the 3 vertices of the super triangle to this point. Okay, now I have the super triangle, all points are there within, and take the first point. And that first point are to be joined with all the vertices so that I will have 3 inner triangles are generated. I will see through an example maybe like this. Okay, this is an example. Now I have got 4 points, 1, 2, 3, 4. These are to be triangulated. These are to be triangulated. And these are all normalized, right? And they are put in the first quadrant. Okay, some coordinates, they are there here. Now I take a super triangle. This is the super triangle. Okay, so 5, 6, 7 is the super triangle, and that is there in the array T. Now take the first point and take the first point and join to all these vertices. So it has generated 3 new triangles. And now what I have to do is, now this triangle is removed from the array, and these generated triangles will be put in the array. Okay, initially one triangle is there, that one is removed and 3 are added. Okay, so these are put in the anti-clockwise, counterclockwise direction. So A triangle,
Sir?
B triangle, and yes.
Sir, not understand. Sir. Please explain again.
When a triangle is divided into 3 subtriangles, the original parent triangle is removed from the array. And the 3 child triangles are kept into the array.
Okay, sir.
Okay, so these triangles are put in some counterclockwise direction, A, B, C, like that. So this triangle 715 and 516 and 617, they are kept in the array. So whenever a new triangle is formed, one triangle will be removed from the array and 3 triangles are added. Means in effect 2 triangles are added every formation. Is it clear?
Yes, sir.
Okay, so now this is the first step. Take the first node and join the 3 vertices of the triangle in which it is there, and so it generates 3 triangles, and original parent triangle is removed and these 3 subtriangles are added to the array. So this is the way I have to continue.
Sir,
Yes.
is it required that we need to take the first node as our required points?
See, I have to gradually include all the nodes. Okay, so I have a series of points. So first I take 1, then 2, then 3, then 4, like that. So whatever
Okay, sir.
way I
Apart
have
from 1, 2, 3, 4, can we take any other points, sir?
Yeah. You can start with 2, or you can start with 4, you can start with 3. But the series of triangles, the series of steps that we do will be different for each person.
Okay, sir. That means I am not saying that
Yeah.
apart from 1, 2, 3, 4, can we take any other arbitrary point to?
No. I am given 4 triangles to be 4 points to be triangulated.
Yes, sir.
My question is, triangulate these given points. 1, 2, 3, 4 are given to you. Why you take a new point there?
Yes, yes.
Am I clear? The
Yes,
question is just to triangulate the given points. You are given 4 points with coordinates 1, 2, 3, 4. So you have to take a graph sheet or suppose something, and you put the points, and you take a super triangle also. And even I can give an assignment. Okay, so I give you 4 points, but I ask you to do in a different sequence. One fill I will give 1, 2, 3, 4, and the 2, 3, 4, 1 or 2, 4, 1, 3, like that. So first you have to, the person who got 2 as the first point has to start with 2, and he has to get the triangles like this.
Okay, sir.
Okay,
Got it. Yes.
okay, like that. Okay, introduce the first point into the super triangle and generate 3 triangles by connecting the 3 vertices to the super triangle to this point. Delete the super triangle from the triangle list T and subsequently add the 3 newly formed triangles into the list of T. The triangles are defined by their vertices in counterclockwise order. And note that at this step, the net increase in triangles in array T is 2. With every new formation, one triangle is removed and 3 triangles are added. So there will be net increase of 2 triangles. Okay, that is over. Now the next point, call it P, is introduced for triangulation. Okay, another point now I take. Now I have to know out of all these 3 triangles, which triangle contains this point. It is in which triangle? Then only I can join the 3 vertices and make the sub-triangles. Am I right?
Yes, sir.
Yes, sir.
So, and subsequently 3 new triangles can be formed by connecting to the vertices of the triangle X. Now the original triangle X is deleted and in T and newly formed angles are added. Thus the net gain in the 2 triangles is 2. But here, first one needs to locate the existing triangle, call it X, which encloses the point P. I have to know which triangle contains that point P. So that is the main thing now needed. So how to search for the triangle X, which contains this point? So how to know whether a given point is within the triangle or not? Okay, there may be different methods. Okay, so here a particular method is used. Because already I have a function written in previously to know whether a given point is to the left side of a edge or not. Is it clear? I have already one algorithm or function available to know whether a point is on the left side of an edge. So using that, I have to find out whether X is within the triangle or not. Okay, the logic is I take a triangle, if it is to the left side of all the 3 edges, then it is within the triangle. Am I clear?
Yes, sir.
Yes,
If
sir.
it is to the left side of all the 3 edges, then it is within the triangle. Otherwise, it is outside the triangle. So that is the way I have to find out. So take the first triangle, check whether it is within the domain or not, within the triangle or not. If it is outside, then you check with the other triangle. Then you check with the other triangle. Like that, I have to do. Okay, so a check is made to see if point P is on the left side of all the edges of this triangle. If yes, the point P is enclosed within the triangle. If P is located to the right of any edge of the triangle, then the search shifts to the triangle which is adjacent to that particular edge. And the process is repeated until X is found. This procedure avoids checking all the triangles. So suppose I have 100 triangles are there. And I have to check it is within the triangle. So for all 100 triangles, we will think that I have to check, but we need not do like that. What I will do is, I will start with the first triangle. Okay, it is like this. Now there are a lot of triangles are there, and P is the point, new point I found, which is to be included within in the triangulation. Now I have to check in which triangle P is. Now I have so many triangles, how to check it? So it takes a lot of time. So what I have to do is, I have to start with the last triangle. Okay, this is the last triangle. I have to check whether it is within this. And I know that it is not within this. It will be right side of this. Okay, so what I have to do is, I have to see what is the triangle formed with this edge. So I will have this triangle. So I have to check whether it is within this triangle. And I will find that it is outside. Then I will see outside of this, okay, right side of this particular edge. So I have to see with this triangle. And when I check with this triangle, that point is right side to this and also to this. So I have to either go this way or go this way. Whichever way you go, it will come to that point. Okay. So if I go this way, I have to check later this triangle, and then this triangle, then this triangle, then this triangle. Once I found with this triangle, it is within this triangle. So I stop searching. If I go this way, it will go in another sequence, but it will come to this particular triangle in which it is existing. Is it okay? This
Sir,
is
for
called as
fourth
search
triangle,
path.
sir, sir, for fourth
Yes.
triangle, the point P is on left side.
So for the fourth point, fourth triangle, this one, huh?
Yes, sir.
So when I check this triangle, it will be found that it is to right side of this particular edge. So then I have to go for this triangle.
Sir, for B to F edge, sir.
What is it?
Sir, for FB edge, sir.
This
FB.
edge.
No, sir. FB. FB.
FB. Okay.
For
So
four,
this
sir.
FB,
Yes,
so
sir.
this FB, it is on the right side. So it will go to this side. And for this FC also, it is on the right side. So it will go this way. So if I go this way, it will come to this 4. If I go this way, it will come to this 4. And after going to the 4 triangle, it comes to the right of CB.
Yes, sir.
Okay. And then I will go to this triangle. And this triangle, it will come within the triangle. So it will be left side of all the 3 edges. So in that way, I have to go on searching till I get this. Once I know this triangle, I need not check with these other triangles. So that is the advantage of going in a search path. Am I clear?
Sir, how for BC edge it is on left side, sir?
That's what I told. We have discussed last time. So we have to find out the cross product, and if the cross
Yes, sir.
product is
Sir, I understood that one, but can you explain in this?
can we?
Can you explain in this triangle, sir? Actually, I understood that one, but actually,
See. For this triangle, right? So I will check whether it is on the left side. So for this, it will be on the left side. For this, will be on the left
sir, for
side.
first,
But for
I am
this, if you
asking
check,
for.
it will come on the right side.
Yes, sir. I am asking for triangle number 1, sir. I am asking for triangle number 1, sir. How all the edges, the point P is on left side, sir.
We go anti-clockwise.
No.
B to
See,
C to A.
this edge is there, right? On every corner you see. Suppose this triangle is there, right? So stand on B, look at C, and whether it is on the left side. It will be on the left side. Then stand on C and look at A, and it will be on the left side. And stand on A and look at B, it will be on the left side.
Okay, sir. How we come to know that we stand B or C, sir?
Yes, what is that?
Sir, how it comes to know that we have to stand on B or C? We can stand on either on point C or either on point B, sir. On this edge, sir. BC edge.
No. See, this is BCA. So you take BC, CA, and AB. Or if you want to
Okay,
take
sir.
like this,
Yes, sir.
BA,
Sir,
AC, and
anti-clockwise we have to go.
Yeah,
Understood. Okay, sir.
Okay.
Thank you.
Okay. So that is the way you have to understand the search path. Yes.
So mathematically, it will
seeing,
cross product will be positive, sir.
Yeah.
If we got a positive cross product, then we
Suppose CA is there, right? CA is one vector and CP is another vector. And take the cross product of these two.
yes, sir.
Okay.
Sir,
Yes.
sir, by seeing we tell that the point lie on one triangle. So what is the needed to that?
No, I will not. Computer will not see it, isn't it? I will see it, but computer will not see it.
If sir P point lie on any edge, then what are the process to find P? Left side.
Okay, if it is lying on the edge,
Yes, sir.
Mm, okay, just I will think about it immediately. I could not say, right? If it is on the edge, I will talk about that.
Okay.
Okay, now this is okay, right?
Yes, sir. Yes.
Okay, so that is the way I have to find out. Okay, what is this, all these things? I am trying to find when a new node is added, I am going to check whether which triangle it contains. Okay, so once I understand that P is within this particular triangle, so what is the next step? I have to join APC and CPA like that. Okay, so this is one triangle and CPA and BPA. So these are the three triangles formed like this, you can see here. Okay, so these triangles are formed. And the next thing, okay, now what I have to do, I have to remove this particular triangle. Okay, ACB is removed and these three triangles are added to the array. But one more thing I have to do here. What happens is, now I have to check on all the three sides. Now suppose this A2CD is there. Okay. Now there are two triangles like this. And by seeing this triangle, I know that this is not a good triangulation. Am I right? This A2C is very far from equilateral. It's complete obtuse triangle, right?
Yes, sir.
So what
Yep.
I have to do is, I have to check with the new triangles whether swapping is needed on all the three sides. Okay, so first I have to check this new triangle and I have to see whether the diagonal is to be drawn this way or this way. Am I clear?
Yes, sir.
So I have to take this ADC, draw the circumcircle and see whether P is within the circumcircle. You will see that P is within the circumcircle. So I need swapping. So I have to draw PD, not AC. So instead of these two triangles, I will have this triangle and this triangle. Okay, I think it is there in the next slide, I think. Yeah, this way. So draw the circumcircle and see that this is within the circumcircle. So I have to make this swapping. So I have to get this triangle, means CPD and DAP. Okay, these two triangles are to be made. Am I clear?
Sir, before that we remove AC, na? Before it we remove AC.
So now here in this is the super triangle for these three triangles, right? ACB, ABC is the triangle which is divided into three subtriangles, right?
Yes, sir.
So this main triangle ABC is to be removed and these subtriangles BPC, CPA and APB are to be added.
Yes, sir.
And after adding that, with each new triangle, I have to check whether swapping is needed on this side or this side or this side. Am I clear?
Yes, sir.
So for all the three sides, I have to check whether swapping is needed. So this particular side, I need swapping. So I have to exchange these two triangles with these two triangles. Okay, that is the way I have to go on. Okay. Okay, that is explained here. The swapping algorithm is now used to update the existing triangulation to a Delaunay triangulation or optimizing of the grid. All triangles which are adjacent to the edges of the triangle enclosing point P are placed on a list in first out stack S. So three are made and the last triangle I have to check for swapping. Each triangle is checked one at a time, starting from the last one in the stack to determine if point P is located within its circumcircle. If yes, then the triangle containing P as vertex and the adjacent triangle from the convex quadrilateral with its diagonal drawn in the opposite direction must be replaced by the alternative diagonal to preserve the structure of the Delaunay triangulation. Okay, it is explained here. I have explained to you. So once the swap is completed, the triangles which are now located to the opposite of point P are added to the stack S. Subsequently, the next triangle is unstacked and the entire process is repeated until the stack is empty. Okay, so those three triangles on all the four sides, all the three sides I have to check. So first I have checked this side, and then you have to check this side, and then you have to check this side. Okay, like this. And it is outside. Okay, so that is not needed. And if you draw here, here also P is outside, so swapping is not needed. Only this side only swapping is done. Okay.
So, sir, whenever we select a new object, the whole process done in total, sir. The whole process is done uh, again and again, sir, for up to the whole matrix
Each
is
node,
completed.
just when a new node is added, okay, first I have to check which present triangles is containing that particular node. And once I understand the triangle, so that becomes the super triangle for that particular node. Okay, so join with the three vertices. I will get three subtriangles. Remove the parent triangle and add these three subtriangles. And when you add these three subtriangles, with each triangle, again you have to check whether swapping is needed or not. Okay, so
So
once
the
you
whole process is done again and again till the whole
till
domain
all the nodes are added. So once the swapping is done, this triangulation is over with the new node, and then you go for the next third node. And again, you
Okay,
do
sir.
all this process. With every new entering node, I have to repeat all the process till all the nodes are triangulated.
Okay, sir.
Okay. And after that, there is last final point is made. Okay, see. So here, suppose 2 is taken and these three triangles are formed. Okay. So swapping check will be done. And after that, 3 will be taken. 3 is within this triangle. Again, these three subtriangles will be done here. You can see this way. Okay. And then 4 is to be taken. And these subtriangles are to be made like this. Okay. And every time you have to check the swapping, right? And once you have done, this is the, here actually one swapping is done. Okay. So here, these these triangles are there, and this is swapped here. Okay, you can just check it later. You can see the figure, properly understand. Okay, so these are the whole triangles are made, but there are so many triangles are there. I actually have to triangulate only 1, 2, 3, 4. So what I have to do, the last point is, okay. So at this point, all 4 points have been used. Thus, the last step to complete the triangulation is to remove all triangles that contain the vertices of the super triangle. Because super triangle points are not there in the given data. I have added them, so I have to remove it. When I remove it, already there are many triangles are made with the super triangle nodes. Okay, so whatever triangles are there with the super triangle nodes are to be removed. Then I will be left with only the triangles which are made with the given nodes. Okay, so here you can see that. Okay, this is the way. These are the triangles. These dotted lines also are there within the triangulation. Now, whatever triangles are containing 7, 5, and 6, all these triangles are removed. And finally, I am left with these two triangles. Okay, this is the final triangulation. Am I clear about this?
Sir,
Yes.
sir, instead of swapping each and every time,
Yeah.
after this removal of the super triangle, we can swap it. No, sir.
No, 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 no. We will be lost many triangles. You can check. If you do it, you can understand it.
Okay, sir.
Right? You cannot do that. Okay. So this is the way it is to be completed. So unstructured grids, which are used in conjunction with the finite volume and finite element. Okay. Schemes were discussed in this chapter at the introductory level. The objectives are accomplished by considering limited number of methods applied to two-dimensional problems. The specific schemes reviewed are advancing front and Delaney's methods. And there are many other methods also, but Delaney's method is the most popular and widely used. And all the packages, the Fluent or ANSYS or whatever it is, they use Delaney's method. It is hoped that a detailed description of each scheme will facilitate the understanding of other schemes presented in various publications, as well as the extensions of the schemes in 3 dimensions. The procedures introduced in this chapter will be utilized to generate the required grids for the application of finite volume schemes in the following chapter. Okay, so this is the way we have to generate the unstructured grid. So we have done
Sir,
domain normalization, and we have seen triangulation. Yes,
sir, the
yes.
FEM method is for 2D or 3D, sir.
This is 2D we have explained. This can be extended to 3D, and we are not doing that because that takes more time. So we want to understand the concepts. Okay, instead of circle, there will be sphere there. Okay, so like
So,
that.
sir, finite volume method we will do
And
in the
now
next
we have
class.
triangles only. In 3D, you will have pyramids.
Okay, sir. Okay.
Okay, triangular pyramid will be there. And it should be as near to tetrahedron as possible.
Yes, sir.
Okay, so that is the way we have to do. Okay. Okay, so next class we will see finite volume method with unstructured grid, which is the next chapter to this. Okay, 18th chapter, I think, in Hoffman second volume.
Sir, finite volume method will also be for 2D.
Finite volume method
Will also do for 2D.
also.
We will also do for 2D, sir.
Yeah, 2D only. We will do in 2D only.
Okay,
Okay,
sir.
it is to understand the concept. It can be extended to 3D. See, we have taken model equations, simple equations, 1D steady or 1D unsteady, like that, isn't it? 2D only we have done. We didn't do
Yes, sir.
3D equations to be solved because the concept is same. It is to be extended to 3D.
Yes, sir.
Okay, right. So shall we go for the story?
Yes, sir.
Okay, today's story, it's nice story. Sometimes, because many times we worry about our weakness. And this particular story is interesting. It says, sometimes your biggest weakness can become your biggest strength. Okay, sometimes it may be found silly, right? Or how can it be like that? So it is a story given. Take, for example, the story of one 10-year-old boy who decided to study judo, and actually is very much interested, and from childhood he is interested in judo, but unfortunately he meets with an accident, and in the accident he lost his left arm. So he want to study judo despite the fact that he had lost his left arm in a devastating car accident. So then he goes to all teachers. He wanted to learn judo like that. By seeing him, immediately they say, how can you learn? You don't have one hand. Okay, like that, all people have rejected him, but he has zeal to learn judo somehow. And finally, he got one Japanese master, and he went to that person, and that person accepted him. And the boy began lessons with an old Japanese judo master. The boy was doing well, so he couldn't understand why, after 3 months of training, also the master had taught him only one move. Okay, he's telling many moves, but he told him to master one particular move. Okay, one particular move he asked him to master. He told many things, but not serious about other moves. But this particular move, he made this child to practice again and again and again to become master. 3 months he asked him to try. And sensei means master. So master, the boy finally said, shouldn't I be learning more number of moves perfectly? And he says, this is the only move you know, but this is the only move you will ever need to know, the master replied. Not quite understanding, but believing in his teacher, the boy, he kept on training that particular move, master it. And several months later, the master took the boy to his first tournament. Surprising himself, the boy easily won his first two matches. The third match proved to be more difficult, but after some time, his opponent became impatient and charged. The boy deftly used this one move to win the match. And he won three people, right? And he didn't understand. Still amazed by his success, the boy was now in the finals. He came to the finals. He himself didn't understand how could I win all these people. And this time, his opponent was bigger, stronger, and more experienced. For a while, the boy appeared to be overmatched. And concerned that the boy might get hurt, the referee called a timeout. So the referee told maybe this fellow may get hurt and better stop the match, and he wanted to stop it. He was about to stop the match when the master intervened, no, and the master insisted, let him continue. And soon after, the match resumed again. His opponent made a critical mistake and he dropped his guard. Instantly, the boy used his move to pin him. And the boy had won the match and the tournament also. And he became the champion. And on the way home, the boy and master reviewed every move in each and every match. Then the boy summoned the courage to ask what was really in his mind. Master, how did I win the tournament with only one move I mastered? You won for two reasons, the master answered. First, you have almost mastered one of the most difficult throws in all of judo. And the second one important is the only known defense for that move is for your opponent to grip your left arm. Right? The opponent has to catch his left arm so that he can come out of that move. But because he didn't have that left arm, they don't have the defense for that. So the boy's biggest weakness had become the biggest strength of him. So that is the story. Thank you very much. Thank you.
Thank you, sir.
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 Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.